Hello, hackers. I'm talking to you from my mom's house. I got stranded over here, so didn't leave in time to make it back to the actual lecture, and the internet here is not good enough to actually Twitch stream right now for some reason. So we're pre-recording this lecture. We're going to Connor will play it live, and then I will see you all tomorrow or Monday for live office hours, and Monday, sorry, for live office hours. All right, anyways, it was very important for me to talk to you about kernel mitigations, security mitigations in the Linux kernel. So let's switch into the screen share dimension and take a look. All right, let's talk about mitigations in the Linux kernel. Of course, you have already hit the ground running. You are exploiting the kernel, but you're running into situations where, you can't execute shellcode, or et cetera, et cetera, et cetera. Why? Because mitigations. Why do we need them? Well, the kernel is a very popular and very high value target. Kernel exploits are extremely important because they are usable in situations where you might otherwise have limited control. So, for example, kernel exploits are very typically present inside as part of a typical exploit chain to take over a mobile phone, for example. And in a kind of more pedestrian way, they're present in a lot of general purpose computing device exploits to elevate privileges and all the stuff that you've been doing so far. So it's a popular target and it gets attacked often. A lot of bugs get found in the Linux kernel and in other kernels. They don't all even get tracked as CVEs for various reasons, from shady to non-shady. But even just as tracked by CVEs in 2021 alone, there have been 149 vulnerabilities in the Linux kernel. So of course, the kernel will get attacked. So what do we do about that, right? Obviously, ideally, we can have a non-attackable kernel, but that's not the case. We're not there yet. We're not going to be there for a very long time. So what we do is mitigations, right? Similar to the user space case where you have now explored tons and tons and tons and tons of different styles of mitigations, we have the same thing in the kernel world. Basically, kernel developers say, okay, we're not going to be able to prevent all the vulnerabilities. It's just not impossible. It's just not possible, right? So let's make it hard for attackers to actually achieve control, to actually do significant damage, even if they find a bug. And most of these mitigations look very familiar, right? The kernel has stack canaries. The kernel has ASLR, where at boot it will place the kernel at a random location. The kernel has NX, right? In a similar way to your user space experience of running into these mitigations as well. If you're interested in kind of the kernel's security posture philosophy, take a look at this link. It's an interesting read, and actually the kernel documentation in general is pretty good if you're interested in kernel security. But the TLDR is that the kernel has a lot of various mitigations, but of course you have spent much of this class bypassing mitigations. So you've bypassed stack canaries by leaking them or jumping over them or doing a number of other exotic things. You've bypassed ASLR in user space by leaking library-based addresses, program-based addresses, etc., etc., etc. You leak a pointer, you bypass ASLR. And it's the same in the kernel. You leak a kernel pointer, you can figure out where the kernel is based, and from there, you can figure out where whatever functions you want to call, whatever gadgets you want to call, exist. Speaking of gadgets, of course, you have trouble executing shellcode in the kernel most of the time because most data regions are non-executable in the kernel. But of course, you'll also know how to bypass that, for example, with return-oriented programming. So the kernel, of course, has this cat and mouse game, et cetera, et cetera. One crazy solution that's upcoming, not really widely deployed right now, is this concept of function granular KSLR. The idea is, aside from just loading the kernel at a specific address, you also have all of the functions in the kernel shuffled around, right? It's an interesting upcoming mitigation that will prevent you bypassing KSLR just by leaking an address. But there's still a lot of things you find out from leaking an address. In practice, function granular KSLR is not the full solution. You can read more about the concept in this article that's linked here of the, if I remember correctly, I linked here the proposed patch, for example. But it's kind of this partial solution. There will be FG KSLR bypasses. It's just another volley in this war. There is also some very, very kernel-specific mitigations because the kernel has a very special security posture, right? Because it lives kind of on top or under all of the user land and so forth, nestled in ring 0. The way that many exploits work when they're attacking the kernel is they trick the kernel into accessing or executing memory that's actually in user space, right? And there are two mitigations that were created to prevent this from happening. One of them is called SMEP, Supervisor Memory Execution Protection. It prevents kernel code from jumping to user space code, right? As you've been exploiting the kernel, you might think, oh, if I overflow the return address here, I can just have it return into my shellcode in my user space application. That is no longer the case. It used to be the case for a long time. But SMEP came out in the last, I should have looked this up when SMEP came out. But let's say in the last 5 years, it got very popular, maybe 8 years. SMEP came out and it prevents kernel code from jumping to user space without going through the correct, return from a syscall, et cetera, et cetera, et cetera, right? So that is closed one exploitation vector, let's say, of the Linux kernel. Then there's a second problem of exploits fooling the kernel into accessing user space memory improperly, right? And another technique was proposed to protect that. Supervisor memory access protection or prevention. Anyways, SMAP prevents kernel space from accessing memory that's in user space unless a flag in the rflags register is set. Now, of course, you can set the rflags register using the stac command in your exploit, but that already, at that point, you already have execution. You probably don't need to access user space memory, right? But what it does prevent is, let's say, an uncareful handling of a structure that's passed through an ioctl containing a user space pointer, causing the kernel to go directly into user space. Now, why is SMAP and SMAP separated? Why can't you say, you know what, screw it, user space doesn't exist when you're in the kernel? Well, that's not realistic. You need to be able to pass in arguments through system calls. For example, the path arguments to open, or the various small structs to other syscalls. And so the kernel needs to be able to access memory in user space, but it does that by using specific APIs to do that, such as copy from user and copy to user, which sets the right flag, the AC flag in the rflags register, does the access, and then clears it again. Simple mitigation, big protection. Now, in all of the challenges in these modules, SMAP and SMAP are both on. Why? Because it's 2021. We're not going to insult your intelligence by having you exploit things that do not exist as problems in real modern deployments anymore. Of course, there are legacy systems that don't have these protections. But in this module, we're assuming that at least these protections exist. KSLR, kind of hit and miss in this module. Some of our challenges have it on, some of them have it off. But SMAP and SMAP are all on. But of course, all of these mitigations, kernel exploitation, like all exploitation, is a martial art. It's a slow battle between attackers and defenders. There's blocking, there's striking. It's all very exciting, and new techniques are developed all the time, both on the offensive and the defensive side. On the offensive side, one response to SMEP, for example, is the use of the run command function in the Linux kernel. Run command in the Linux kernel just takes a string, splits it by spaces, and runs it as root in user space. Right? Obviously, that's a very powerful primitive. It's a kernel function. So if you have kernel code execution, and you can call a function with a controlled argument, boom, run command is your friend. You don't have to return to user space. You don't have to do a lot of things. You can just run a command as root. If you're interested in how that actually works under the hood, you can look up the source code on Bootlin. It's an awesome resource for looking up kernel concepts. That's a link to the latest version. I think the version that we're running in pwn.college right now is 5.4, but it's very analogous, right? And you can actually change Bootlin to look at the correct version that you're interested in. So this is just one kind of bypass. I mean, it's very cheap as a bypass. It just runs commands, but it's quite viable. So all of these exploits that used to have to jump back into user space code or do complex swap could just potentially call run CMD. Obviously, there are other advanced kernel exploitation techniques, but for the most part, for this module, you are really mastering the basics to be able to operate in the kernel successfully. All right, let's exit the screen sharing dimension. That is what I wanted to talk to you about regarding kernel security mitigations. And I wish you good luck, and I will see you soon as I have internet good enough for streaming again. Good luck.
All right. So enough of pretending to be on, I guess. Is my audio still working? I think I had to unmute it. Let's see. I think so. Maybe. I don't know why my phone is so behind on the stream. There we go. All right. Good enough. All right. Yeah. I was wondering if anyone would notice before Jan said that this was a pre-recorded video by noticing that this was streaming at 4K, but no one noticed, so All right. Wait, someone says we can't hear you. No, I see this green bar moving. It must be. Did someone confirm my audio is working? I could have sworn I just heard myself. Okay, audio is good. All right. So, yeah, unfortunately, as Jan said at the beginning of the video, he is stuck at his mom's house and was not going to be able to make it in time for class. And unfortunately, her internet's not good enough to stream from right now. And here we are. Okay. That being said, I can't guarantee it, but I think he's planning on doing an office hours tomorrow, I believe. No guarantees on that, but I think that's his plan. So this is going to be probably a relatively short class. Hopefully he'll also do like a meme review tomorrow or something. I'm not going to take that over from him. It's the sacred Jan meme review, and plus I haven't prepared my such a meme review anyway. So we'll leave that to him. What time, if you have an estimate? Hopefully he can give an estimate today, but I don't know. Okay, so anyways, I did a 2-hour long office hours yesterday, so I covered tons of stuff there, but I'm happy to answer questions for a bit anyways today if there are questions. So if anyone has any questions on the challenges or any concepts or anything like that, feel free to ask and we can look at it. Okay, so there is a question. Several questions. So the first one I see is level 5. How do I find the actual win address? When I pass the win address found by objdump, it's something like kernel tried execute NX protected page exploit attempt. Okay, so let's quickly address that. Because I think this is an important concept that I don't know if it's directly covered in any of the lectures. Okay, so if we start up level 5, just to kind of demonstrate this. Okay, that is not what I want. SSH there. Okay, so if we VM start, VM logs, sit here, watch stuff boot, blah, 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 blah. I guess actually for doing objdump, we don't need the kernel to boot, but if we look at this challenge and we do our standard objdump reverse engineering. So we run objdump -d mintel challenges baby kernel level 5 0 ko. And let's pipe that to less. So if we look at this and we just search for win, we're going to see that there is a win function. So actually, there's a few things to note here. So there is a win function that we can see listed here, as well as all of these device ioctls, blah, 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 blah. We can see all sorts of code. Something to note about these kernel modules and the way that they're compiled is that they have significantly more relocations in these binaries compared to the challenges you've seen so far. In fact, I don't know the binaries we've shown so far have had any of these sorts of relocations yet. So what do I mean by relocations? So if you look at this instruction right here, where it says call win plus 0x13, if you look at just the raw bytes of this instruction, something should be standing out to you. This does not look normal. We're doing a call instruction and all of these bytes are 0. And if you look at this jump instruction, all of these bytes are 0. And if you look at, I don't know, there's probably several things. I think this move RDI, for instance, right here, all of these bytes are 0. There's going to be a bunch of zeros littered throughout this assembly if you just look at this with objdump. So we need to change our flags real quick. So rather than just doing objdump -D and then -M intel to do Intel syntax, we need one more flag if we want to actually look at this in a slightly more reasonable way. And what that flag is -R for relocations. So if we look at this again now and go to win, we're going to see a bunch of stuff peppered throughout this code now. So for instance, we can see here when it's doing this call and a bunch of zeros as the address, objdump is now printing to us that there is this relocation that needs to happen where what it's really getting ready to call is prepare kernel creds. And the issue is that it has absolutely no idea when we compile this where in the kernel prepare kernel creds that function is going to be. So it just puts in a bunch of zeros, and then when this kernel object gets inserted into the kernel, all of these need to be fixed up. All of these relocations need to occur. And when it's inserting it into the kernel, it's going to fill in the address of where this is, or maybe the RIP relative address, I'm not sure. But it's going to fill this in at runtime. So that is one thing to note. And I believe if you look at this in IDA, it's going to automatically realize this is a relocation. And when it does the decompilation or even just the assembly, it's going to tell you that it's doing a call to prepare kernel creds. It's just that the default objdump doesn't do that, I guess. Okay, and then the other thing to note is that if you're just passing in this address right here, this bunch of zeros 5B, in exactly the same way that when we compile this kernel module, we have absolutely no idea where prepare kernel creds is, we also have absolutely no idea where win's going to end up. These kernel modules are basically, it's kind of like a plug-in system to the kernel, and we're loading this in, and it's going to get located somewhere. I mean, probably this 5B is going to be the offset from some page boundary or something. I'm not entirely sure on that. I would guess that that's true. But this is definitely not the address. So if we want to actually get the address of win, the simplest way to do that is to boot up the kernel in practice mode. And if we connect, and then we run tail to get the very end of proc k allsims, and we run this, okay, you're going to see here we have a bunch of zeros, and the issue is that we're running this as non-root. If we rerun this command with root, it's going to give us these addresses. And here is the actual address of win, where win is located when this gets loaded into the kernel. I think, was that 6D the same for objdump? But either way, it's getting offsetted by this. 6D, let's see. Win was 5B, so it's even shifting it another 10, I guess, hex 10. But yeah, this address is absolutely going to be correct, because if someone else wants to link against this symbol and be able to call this, I mean, the kernel is keeping track of where all these things are located, and it's showing that to you through proc k allsims. All right, so that is that question. So yeah, if you're passing in that address with a bunch of zeros, that's why it's going to say kernel tried to execute an NX protected page exploit attempt, because you're accessing probably like the 0th page, which I think is mapped. Maybe it's not, I don't know. But either way, it's not mapped executable, and exploit attempt, blah, blah, blah. How to inject shellcode in debug using GDB. Okay, we can talk about that. And then there was also a question, we could talk about the C types thing you mentioned in the Discord server, or should I just be using C? So I would recommend using C, but you can use, I believe you can use C types. Let's just try this real quick. Eventually. Yeah, inside the VM, IPython is very slow to boot, but as soon as it boots, it's a reasonable speed to use it. It's just executing so much code that's being emulated. Okay, so if we import OS and then import F control, and then OS open Pwn.college. Oh, I hit tab. Tab also executes a lot of code. Tab is dangerous. I'm just going to hit Control C until it decides to give up on doing all that computation. Proc .college, and we'll open it for 0. This is the FD. And then if we want to do F control, IO control, this is the function. This is how we could call into IO control. We need to pass it an FD, a request, and then this argument. And then the issue that is being discussed is how do we pass a pointer to this? So apparently you can't just pass an integer. I mean, we'll try that real quick, but I don't think you can. If we do FB 1337, and then let's just try this. This would be that padding function. Just in case, let's SSH on another terminal and look at VM logs. Okay, so we saw that the device open happened. And this is, I guess, the error that we get when we do that. If you did this in C, this would call into bin padding. Probably not what you want to call, but clearly doesn't work in Python. But there is a module in Python called C types for interoperating with basically C code. So for instance, we can do something like, we can basically pull in libc. So we can do like ctypes.cdll, and then we can do libc so6, and this will just load in libc. So now we have this libc handle, and we can, for instance, grab IO control, which it says is this function pointer. And we could do libc IO control fd1337, and probably we can just pass it like this. We might have to give typing information to this stuff, but let's see. Return 0, which sounds pretty promising. And yeah, we can see that device IO control just got called with those arguments. So that would be one way to do this within Python. It's possible that there's a way to call into this and give it a pointer, maybe, but this is, you really don't want to use C for some reason, but you want to interface with C, basically. This is a way you could do that. Okay, so that answers that question. Okay, so the question of how to inject shellcode and debug using GDB. Okay, what level lets us do shellcode? So this one calls a function, right? So probably the next one lets us pass shellcode, if I remember right. Okay, so yeah, let's look at how we would debug shellcode on level 6. Yeah, level 6 is shellcode. Awesome. Okay, so if we do VM start, and then we'll just watch the VM boot for fun. And we can see that it tells us we have access to open, write, and close. And the character device will execute any shellcode that you write to it inside the kernel. It's very convenient. Okay, so let's do a VM connect, and let's just quickly boot IPython so we can wait our 15 seconds of IPython launching. So there's another question while we're waiting on IPython to boot. How to check if KSLR is enabled in a machine where you are rootless? Since in practice mode KSLR is disabled, true, I wasn't able to see KSLR addresses to think in different approaches until I reached the correct solution. Okay, so level 10 is the only level where we actually enable KSLR. So the simplest answer is just say, that's how I guess you check, but from within the VM without root, how do you check? I'm not super sure I have a good answer for that. One way to do it, this isn't exactly from within the VM, but if we run VM logs and we scroll to the very top, it will tell us, and unfortunately, we can't see this because my camera's covering it. Let's see. How can I do this? Let's just run head temp VM log, which is really where this is. What? Echo. How do I make head not like reset? What? Oh, I have an idea. That'll also be an issue. How do I get this to be? Okay, idea. Just trying to work around this camera creatively. Emacs it. Oh god, this is going to be slightly crazy to read, but it'll be good enough. Okay, we can see here when we boot this, that we can see that at the very end of this, basically the options for booting this. So we're specifying all sorts of stuff that relates to kind of what the root file system is, and this is how we implement it. It's sharing with the Sharing with the container, we say kind of like what the console is, just a bunch of boilerplate stuff. We say what the entry point is once the kernel boots, what is going to be PID 1. We specify that, hey, this is going to be PID 1. And at the very end, we specify no KSLR. So on level 10, when you boot this machine in non-practice mode, you will see that this is not here. As for how you can do it actually within the VM, I'm not sure. There's maybe a way to do it, but I do not know what it is. Yeah. Okay, anyways, back to level 6. Is KSLR going to be in Toddler 2? If I had to guess, we would probably have challenges with and without it. I can't definitely commit to that, but probably we'll have both. Yeah. I mean, the basic idea of KSLR is exactly the same as ASLR, which is that you need to figure out some sort of leak, right? You need to leak an address, and then you can know where everything is relative to it. At least until there's function granular KSLR, but that is not currently a default compilation option, so maybe next year the students in this class will be forced to deal with function granular KSLR. Every year, you know, the class just gets more difficult because there's more security mitigations. Okay. So we were looking at level 6, I think. So if we want to basically debug some shellcode. So if we, let's see here. If in one terminal we run VMDebug, this is going to connect into GDB, and now everything is paused, basically. Everything is just hanging. So if I hit enter, I just hit enter. You can't exactly tell that. Nothing's happening. The system's not responding because we're basically broken right now. We can start inspecting the state, etc. If we instead continue, now we're back to being able to use the system, and we can see all those enters got processed. So if we want to debug some shellcode in this level, what we could do is import OS, and then fd equals OS open pwn.college, and we need to open this for writing. We'll just open it for both, I guess. Read write. And then if we do os.write fd, and I believe that this right here is going to be sending shellcode, and the very first byte is going to be an XCC, which hopefully by now you know XCC is a breakpoint. If we send this off, we can see that something's hanging. It's possible we crashed the kernel or something, but let's see here. Oh, did we crash the kernel? Interesting. That does not work, it seems. Okay, here's how we can check what just happened. We run VM logs. We can see something not good happened. Where did we crash? I need to fix this so that it's not printing like double of everything. Okay, so we're executing over here, which looks like probably the start of our shellcode. It says bad RIP value. What is it complaining about? It's not super clear. And it's really unfortunate that we have basically duplicates of everything Where? Bad RIP value. I have a guess of what that could be. Okay, let's start by, did we actually crash the kernel? Are we done? Yeah, it seems like we're done. Okay, let's reboot the kernel. VM restart. We're gonna have to start IPython again. Okay, there's also a question while we wait for all of this to start up. Is there a similar brute force approach to KSLR like ASLR when you have partial overwrite? Or is it more infeasible? I believe the approach would be the exact same, yeah. If you have the ability to partially overwrite saved RIP, I don't see why that wouldn't work. Yeah, so either a partial overwrite is a solution, or a leak. It's kind of, yeah, I believe that would work exactly the same. Of course, until there's function granular KSLR. Oh, but you say a brute force approach. So as in if we need to like guess at, if we have to do like a 4-bit brute force or a 12-bit brute force for some portion of that, that's going to be an issue, maybe. It depends on how we crash. I've noticed that there are some ways in which we crash where we actually crash the entire system, and there are some ways in which we crash where it just aborts the syscall and the system continues executing. If it just aborted the syscall and the system continued running, then in theory you'd be able to do a kind of like a brute force approach. But if we actually just crash the whole kernel, then yeah, it'd be game over. I'm not entirely sure what causes some crashes to not actually crash the whole system, but that would be an interesting thing to explore, because if we could just do these partial crashes, you could imagine doing a bunch of syscalls that are just kind of doing the brute force. Okay. So if we launch IPython again, and we will do VM debug, and we'll continue. So this approach did not work, which is unfortunate. Okay, let's import OS, and then let's do fd equals os open proc pwn.college oso read write. And then let's, instead of writing CC, let's just write return and see that we can execute shellcode. Because the way that this shellcode is executing is it calls into our shellcode. So if we return, we're going to be back to the caller of our shellcode. So if we use, let's just import pwn. Is that going to be a slow import? That might be a pretty slow import. I will ask Linus about that crashes. Yeah, maybe he'll answer. Okay, let's do pwn context arch equals AMD64. And then pwn context, or no, not pwn context, pwn.asm ret. Oh, does this, I saw someone in the Discord mention that this doesn't work. How does it not work? Dev standard in, no such file or directory. Wait, really? We don't have a dev standard in? Oh, what do we have? We need to bring back dev standard in, apparently. Huh. I did not know that dev standard in was not the default behavior. We will have to figure out how to turn dev standard in on so that you could do this inside. But we can do it on the outside, no worries. Incognito, sh hacker dojo pwn college. We will do it on the outside. I wish I just knew the bytes for ret. I should know it, but unfortunately I do not remember what the bytes are for ret. Just a little embarrassing, but we'll roll with it. Pwn context arch equals AMD64 Pwn ASM ret. C3. Okay, that does look familiar. So do we have FD? We do. Okay, let's do os.write. And on this one, let's do VM logs C3. D. C3. We want to make this a byte string though, just so that no crazy Unicode things happen. Let's, okay, so we're looking at the logs. We can see that the open happened. If we write this, you can see that it received a byte. That went through and nothing crashed. I guess that doesn't exactly confirm that we just executed our shellcode, but we can at least see that we made our way into device write. So we previously tried sending a CC, and apparently this debug system is not smart enough to pick up on that, which is unfortunate. But we can still debug this. We just have to be a little more creative in how we do that. So if we hit Control-C to break the system, and we break at device write, actually we don't have the address of device write right now. Let's continue. We'll go here, we'll do sudo tail rock klsims. This device write, we want to break here. So we'll break again. We will set a breakpoint here. And we will continue. And now if we run this os.write C3 again, we will see that it is hanging. The logs don't seem to indicate that we crashed. And of course, if we go to GDB, we see thread 2 hit a breakpoint. The reason it says thread 2 actually, in case you're wondering, is we have given this QEMU instance 2 CPU cores. So the way that this GDB is representing that is as 2 threads within GDB. So it looks like on the second virtual core, we hit this address. So if we do x/8i RIP, we can see a bunch of code. And we'd probably want to look at IDA to kind of compare this assembly with decompilation, kind of go back and forth to figure out exactly where we want to break. But we should be able to just kind of figure this out on our own. So if we look at this print K, this is where it's going to print that debug message that happens when we enter write. So for instance, if we look at this string, we will see that it is this format string. And this initial part basically says that this is like an info message, in case you're wondering. And then we can see copy from user happens. And then ultimately what we're looking for is like a call register. Or in the case of the kernel, it has a, I believe it's just a Spectre mitigation, but maybe it mitigates other things as well. This mitigation here, where instead of doing call RAX to call do this indirect jump, what we're doing here is we're effectively doing that, but that with mitigations enabled. If you're curious about that, you can check in the Discord. There was some discussion on that, or Google around for Spectre mitigation and copy and paste this in. Basically what it's doing is it's doing a call RAX, but it's hanging the CPU's speculative execution engine so that there aren't side effects. It's a whole interesting thing that I'm sure will be covered in that future course that Jan was talking about with the baby arch challenges with architectural bugs, basically. If you haven't heard of Spectre, look into it, but it gets into this speculative execution thing where you can trick the speculative execution engine into executing some other code speculatively. It's not actually executing it, but it's speculatively executing it to see, because it thinks that this is the path, and there's all sorts of, one of the most biggest overhead things in computing is predicting where we're going to jump to. And rather than just sit and wait for where we're going to go to be resolved, it just speculatively guesses where we're going to go. And it turns out that that has consequences on the cache. So even though all of the effects of that speculative execution get unwound, it doesn't unwind the effects on the cache, and then you can do timing stuff, and there's a whole class of bugs related to doing speculative execution and speculatively executing code and getting the results of those speculative execution results. It's a crazy world. Very interesting stuff if you're interested in reading up on it. It's kind of a whole crazy class of side execution or side channel vulnerabilities. Okay, anyways, that is what that is, but this is where we want to break on. And I guess we can kind of very quickly see what this is going to actually look like. So if we set a breakpoint here and then continue, we can see that if we print RAX, this is going to be where the shellcode is. So for instance, if we do x8gx RAX, there's a whole bunch of stuff here. I'm guessing there's uninitialized data there. If we print these as instructions instead, x8i RAX, we can see that the very first instruction is going to be a ret, which is what we pass to it, which makes sense. And then, yeah, I guess there's a bunch of uninitialized data there, which is probably why we were crashing the kernel, or maybe, I don't know. But okay, so let's step into this just so we can quickly see what this indirect thunk nonsense is doing. So it's using lfence. Unfortunately, I don't know the details quite well enough. Lfence has to do, you'd have to look into it. I believe lfence has something to do with stalling the speculative execution engine in some way, or I don't know, it plays into this in some way. You have to read about it to know for more. And then we do this jump RAX. We can see there's stuff after this, and this also has to do with preventing the speculative execution engine from actually executing. Jump RCX. Oh, this is the next thing. Data exchange AX. I thought there was going to be like a jump back to itself. I'm not totally sure. Somehow this stuff relates into stalling the speculative execution engine. That and this. I don't know. We'll ignore it for now. That is a future class. So if we step and then it looks like we're about to do that jump RAX. We step. Now we can see that we are executing in our shellcode. And moral of the story is, once you have this address, you could just set your breakpoint here, and this is how we could now start testing stuff. So for the person that was asking about how do I start debugging my shellcode, basically, apparently we can't just send a CC byte, which is unfortunate, and I'm not entirely sure why you can't. Somehow QEMU must not be tracking like arbitrary, like I'm guessing because in theory we could be running GDB within this QEMU instance, and then that should be handling it, and I guess it doesn't propagate all the way out to the system's breakpoint handler. I don't know. But we can just step through instructions until we find this address, and now we could just always break here, basically. So even if we crash the system, next time we boot the system up, our shellcode should be here again. And that might be slightly different for every single instance of this challenge, but specific to your instance of your challenge, once you have this address, just set your breakpoint there, and this will always be the start of your shellcode. Okay. You can just print out pwn ASM results and save them to a var. Yeah, so you can generate your shellcode for now outside of the VM and then run it inside the VM. For now. Hopefully we'll make it so that this pwn ASM will work in the future, because apparently we need def standard in, because pwn tools is expecting that to exist. but for now, just create it outside. I created a huge monster that starts the VM, waits, connects to logs, create a C code, compile the C code, connect to the VM, execute the C code, collect output via logs, and cry because no flag. Yeah, you can start automating your entire handling of this. And I showed that a little bit in my office hours yesterday, how you could start writing pwn tools and execute that from the host rather than inside the VM to kind of run arbitrary C code. So you have to check out that office hours if that's what you're interested in. But long story short is that there is a VMExec command, which will probably be very useful for that, which allows us to run arbitrary commands inside the VM. So for instance, VMExec ls, which is going to hang because we're in GDB, we continue. It will bring back the results inside the VM of ls. We run hostname. It will tell us the VM's hostname because it's running all of these commands inside of the VM. Okay, another question. Is the plan for the class next fall, or is it too early to say? And I think this might have been addressed, but will it be a graduate level class? So the details on that class haven't been really finalized. I'm not, it's hard to say when it would run. It would almost certainly be a graduate level class, though. The issue is that we teach this class in the fall. I don't know, maybe Jan would be down to teach multiple classes in a semester, but I can't speak to that idea. Please, can you help on level 11? Level 11, which is the second to last level, which I guess 6 people or 5 people are currently on level 11. I will give a huge hint, or a decent sized hint about level 11. And what I will show you is that if I do ls-al proc self mem, this is a thing that exists. This thing is very useful. I mean, there's probably all sorts of solutions for level 11. But this existing, it's very cool. Very cool thing. You'll have to read all about it. But this thing, very cool. Level 11. Fortunately, this thing will not help you on level 12. But so someone says read directly from that, so you can't just cat this out. It's gonna complain to you. And the reason you can't just cat it out is that it has a very specific interface which requires you, I don't know exactly what the interface is, but I believe that the interface is that you need to seek into this thing, to seek to a particular address, and then you could read from it. You might be able to mmap also, but if you Google for proc self mem, proc self mem, wow, people are so generously showing you how you can read from this thing for yourself within Python. So yeah, that is how you would do it. But yeah, that is your very huge hint for level 11, or a direction to think about for level 11. Remember, when you're executing code inside the kernel, you own the system. Like the kernel is, I mean, I don't know if there's anything more, I mean, I guess there are lower level details that even the kernel can't affect, but very few things. And certainly in the context of processes, the kernel is all powerful. Someone asked about using Yon85 on Stack Overflow and watch the site implode. Someone says my VM crashed when I do chmod on level 6. You should probably just step through that shellcode Oh, wait. I think I see a potential issue. Don't make syscalls inside the kernel. The syscall interface is how user space can call into the kernel. If you're in the kernel and you perform a syscall, it's like the kernel trying to enter the kernel to do a kernel action. I mean, you could imagine the kernel being able to handle that use case, but it doesn't. I will say that there are lectures on this sort of topic of what level 6 is and all sorts of other shellcode sorts of things that you might want to do. And you could think about what previous levels have done. We have this win function. What if you made your shellcode be that win function? But if you really wanted to do chmod, I mean, you could do it. It's going to be harder. If we look at Elixir, Bootlin, look for the kernel, and we search for do chmod, this is going to be, where is chmod going to be defined? Do open, but it's in the same file. Here, do chmod. Oh boy. Somewhere in all of this source code is the underlying function that'll handle chmod. Don't know how you find it without grepping for a define. Oh wait, here. This looks cool. Chmod. Yes. Well, it's just going to bring me back here, isn't it? Chmod. Where is this? Oh, it is actually defined here? Oh, it is. Sys.chmod. Or, I mean, this is a header file. Find this too. You could call this if you really want to. This is certainly not our intended solution, but it's an open-ended problem, and this code exists in the kernel. You could call into this if you really want to do that, especially since all it takes is the null-terminated string that is the path, and the mode. It looks basically just like the syscall interface. But yeah, you cannot do a syscall instruction. So if we can't do chmod, we do open, read, write. Those are still syscalls though. Yeah, so someone in chat saying, think more along the lines of making yourself root. There's a reason these previous levels have been upgrading your process to root. This is kind of the standard line of attack within the kernel, is that you just elevate your process to root. Now you can do all sorts of stuff in user space in the way that you're comfortable with. So that is kind of a more intended route, but it'd be cool to see if anyone goes down these syscall-esque routes and pulls it off. I mean, it probably isn't too difficult, but in fact, if we grep proc klsims for, what's my order? I always forget which goes first. Okay, here. So it looks like just that chmod is not a symbol that the kernel is willing to tell us the location of, which means it's not, I don't know, there's some macro for exposing what's going to actually be here, but probably one of these things will work, like chmod common sounds pretty cool. Chmod common. Yeah, this just takes a path and a mode as well. I would expect that this would work. You just call this function, and we can get the address of it we just saw. It's right here. Call into here, set up our arguments correctly, and probably this will work. Now there's a chance that it won't work. Maybe there's some weird, it expects to be called into from a very particular way and we're not calling into it in that very particular way, but I don't know, I would expect this would work. without really knowing for sure. All right, are there any more questions before I start wrapping up this extended Q&A? I tried exactly that and was getting seg faults, unfortunately. Yeah, so unfortunately, I mean, I haven't tried this path. I don't know why it would seg fault. I just don't know enough about this. It'd be cool to really dig in, though, and figure out why this approach wouldn't work. But we've discussed approaches that definitely will work. All right, any final questions? Only if you can talk about level 12. So the only thing I'll say about level 12 is there's a lecture video on ideas related to level 12. So something to think about is that even when a process is gone, who cares? This is just like a kernel concept. And we're the kernel. Bring the process back if you really want to. You have arbitrary code. You're in control. I mean, that's probably not what you actually want to do, but it's the sort of thinking to have when you're executing as the kernel, that you're all powerful. Bring the process back from the dead. It's probably going to be more difficult to take that approach, but that is definitely the line of thinking. All right, I am going to end this then. Hopefully, Jan will be able to announce like an office hours or something for tomorrow. Yep. All right. See you, everyone.